many people don't have their accreditation project? Don't have, raise your hands, I'm trying to get an idea. Can you try to start getting on it? Because honestly, I'd like to get this done before the break, Thanksgiving break. I want to make sure everybody's got something. And I'm pretty good about giving you an okay to do dorming or anything. So the only thing you have to do is see me or send me something. How many have it? How many got it? One hand, please.
Don't or have they?
How many have been assigned a project? So all right, it's about 40%. Please, I'd like to get everybody assigned and done with it before the break, all right? Before Thanksgiving break. When's our test again? This Wednesday?
Can you post quiz solutions?
Did you send me an email about that?
No, but I can.
Please do, and I will. All right, we got test this Wednesday. I got another test in the other course I'm teaching this Wednesday. Yes, sir.
What is the last topic covered for the upcoming test?
S parameters. Yeah. All right, so we got 2 tests on Wednesday. I thought so. And I'm trying to think what else. These meetings are just eating me up. Afternoon and morning meetings. Okay, first I'll take questions about anything you have right now. Everything from the last test, the stuff we covered till now is the pertinent material. Be responsible for everything. So if I ask you something that's, you know, a basic wave equation problem, it's still legal for me to do that, but the weight is going to be in the second, in the stuff we've covered since the last test. But it will probably include antennas because think about radar and that. Antennas are involved in that and the Friis transmission equation, okay? Now open the floor. Which ones do you want to talk about? I got a lot of email. I'm not sure if everything's answered or not. Why not S parameters? That was the last topic. Did y'all do those problems? All right, do you have a question? Yeah. Yeah. Why not? Yeah. And if you want to, bring rotated Smith charts, okay? Bring your own rotated Smith charts if you like them.
Will you have them if we don't?
I'll find a way to, yes. I will print. Could you send me an email about that too? You know, my father used to say this, the dullest pencil is better than the sharpest mind. And if your mind ain't sharp, for goodness sakes, use a pencil, or in other words, write it down. I'm just telling you, I look at my email box. This is no joke. Between this class and the time I walk into this class and the time I get out of my 2 o'clock class. And I got a couple hundred emails in there. All, some of these important, you know, the red flag on the thing must be done by 5. It's like, then I get these urgent meetings that aren't urgent at all. I'm ignoring them. Somebody's canary died or something. Anyway.
Can we do 1026?
Yes, we can. 1026. By the way, the Board of Trustees are in town this week, so Friday, I may not be here. Giving you a heads up, you may not have to be here. I'm trying to do this in the most professional way possible. I don't know if I'm going to be here, but worst case scenario is I won't be here because these meetings go long. So fellas, if I'm not here, is anybody going to be mad? No. You're mad? Don't hurt him. I'm going to try to be here, all right? But these things are getting longer every time.
Will we have a quiz Friday?
I'll make one out just for you. No, we won't. Which problem was it again? I'm sorry.
1026. I have it right here if you need it. Page 67 in my book.
Let's see, you got 25 series, 50 ohm shunt. Here's what this looks like. This is a good problem, by the way. These are the problems that people mess up. So they've got a 25 ohm resistor here in series, and then they have a 50 ohm shunt resistor here. And then they've got the transmission line. Or I should say, or it could be the microwave circuit, but it's really a transmission line. And is Z naught on this 50 ohms? Is it? All right, so it's 50 ohms on both sides. I want to tell you one thing. This doesn't have to be 50 into 50. This could be 50 into 100. You follow me on this? They don't have to be the same characteristic impedance. It's important to understand that so you don't get in the habit of just assuming that. All right, now with this one, this is going to be, is this port 1 where the series? All right, this is port 1, this is port 2. And again, that means that V1 plus is going into it, and V1 minus is coming out. Here, this is port 2, and V2 minus is coming out, and V2 plus is going in. So when you look at this, the first parameter we want is S11, and that's V1 minus over V1 plus, given that V2 plus is 0. I want to make one comment. If there were more than one port, or one input, one output, if you had two outputs, for instance, then it'd have to be a V3 plus would be 0, or V4. Everything else has to be 0 as far as an incoming signal. There's only one, and that's the one coming in on port 1. This, by the way, does everybody see if this is 50 ohms out there matched? There's nothing coming back at this place. No, there's no signal returned into port 2, correct? Nothing reflected that comes back. So we can just say that S11 here is really just the reflection coefficient at port 1. And that would be here. And that reflection coefficient would be the impedance you're going into. Now I want you to see this without me redrawing it every time. Can you see if I'm looking this way at the impedance? I'm going to have 25 ohms in series for sure, right? And then I have 50, and it's in parallel with 50. 50, 50 is 25, so 25, 25 is 50, correct? Now just take a look at this. If I got 50 going into it and I came from 50, well, the reflection coefficient would be 50 minus 50 over 100, or 0. So here, by looking, it's 0. All right, that's S11. Now, that means the transmission coefficient is going to be equal to what? Pardon me? 1 plus the reflection, right? Or it's just 1. Agreed, class? Just so everybody sees this, right? Now, our next thing we're going to get is S21. And S21 is equal to V2 minus over V1 plus, given that V2 plus is 0. And this is really the amplification here. I call it the gain or the forward gain. This is how much of that signal comes out. It may not be a gain. It's actually going to be a loss in most cases. And this for sure because of the resistors. But if we had an operational amplifier or if we had any kind of a high frequency transistor amplifier there, that could easily be it could be a gain actually that we get out of this. So that's the transmission coefficient. Now S21 is typically, what I like doing, is saying I know it's going to be the transmission coefficient right off the bat, transmission coefficient at port 1. Do you all agree with that, class? That's how much of the signal gets on to the filter, if you will. How much goes from here to here that isn't reflected. All of it's not reflected. Agreed, class? It all goes. Now, of that signal, what happens? It's divided down between 25 and 25, right? Can everybody see exactly 1/2 of that signal will be right here on the output? You all see that? Give me a show of hands. Make sure. Y'all with me on this? Okay. So this is tau 1 times really, technically be the resistive division, but in this case we can see it's 1/2. So this is 1 times 1/2 or just 1/2. So that's S21. With me? This isn't a hard problem, but it's a problem that'll make you think about the port 2 business. Now for port 2, when I look at S22, that's V2 minus over V2 plus, given that V1 plus is 0. So nothing's coming back at port 1. And in other words, if I put a short circuit over here, then I'd have a reflected wave to worry about. With me? We'll do one of those, but I don't. It's matched. So nothing's coming back on port 1. When I look at this, that means S22 is really the reflection coefficient at port 2. We're at port 2 here. What impedance do we see looking over there? Now think about it. I know I've got 50 in parallel, don't I? I got 50 in parallel with 75 ohms. Do you all see that? So the actual impedance I'm going to see there, Z looking into port 2, is going to be equal to 50 in parallel with 75. And that's 1 over 50 plus 1 over 75. And that comes out to, trying to think of the easiest way to do this. 30, is that 33.333, I guess, ohms? Is that right? 50 times 7, pardon me? Over 50 plus 75.
It's just 30.
It's, yeah, it is just 30, you're right. So it's going to be, so going into 30 minus 50 over 30 plus 50, and that's going to be minus 20 over 80, or minus 1/4. Is that right, class? With me? That's going to be the reflection, because it's the impedance you're going into 30 minus the impedance you came from 50 over the sum of them. So that's going to be a total of 80. So it's minus 1/4, and that's S22. And then that means which is the reflection coefficient, the transmission coefficient on port 2 is 1 minus 1/4, 1 plus the actual reflection coefficient, so it's 3/4. And now that I have the transmission coefficient, I can get S21. Is that a eraser in front of my eyes? The rag. They had an eraser here the other day, didn't they? Operative word is had. Well, those don't just walk away on their own. But. So here, we're going to go ahead and say that now S, and this is S12. The 2 indicates where the signal's coming from, the 1 where it's going to leave. It's leaving port 1, coming from port 2. S21 is going to be V1 minus over V2 plus, given that V1 plus is 0, and it is. So here, that's the transmission coefficient on port 2, right, times, and here we do the voltage division. If you take a look at this, I know whatever voltage gets on here, the 50 ohm I don't care about. That affects the transmission properties. But then when the voltage is plus to minus here, right, that's V2 prime, it's going to be use voltage division, and it'll split between this 50 and this 25. So it's really going to be 50 over 50 plus 25, or 75. Or 2/3. So this is tau 2 is 3/4, right? Times, and this is 2/3, or this is 2/4, or 1/2. And that means the S parameter matrix for this, if we were to put it up here. Let's see, S11 is 0. S21 is 1/2. S12 is 1/2. And then S22 was minus 1/4. Is that what the book has? It's not hard to do. Just go through the steps methodically. Here's where it gets a little crazy, a little more work. If it wasn't this circuit, but it was this circuit, something where I had minus J, say 50 here, then you get complex numbers. And all the S parameters possibly become complex numbers. You're probably going to get something like that. Can I be any more clear? All right. So prepare for that, all right, when you do this. Just to give you a heads up. It's more difficult only because complex numbers mean more calculation, or that you've got to enter a real and imaginary part or a magnitude and an angle. And some people are kind of rusty at this, by the way. They haven't done a lot of this since circuits. And just, you know, you guys got powerful calculators. They all can do this. Make sure you can do it. Okay? Fair? That's that problem. By the way, what are we ranked now? Does anybody know? Football rankings, not basketball. They should be out by now, right? No. I mean, I'm talking about college football rankings. All right. We're 16? AP is pretty close. 16? I was sad that game. I thought we were going to win. Another one, guys? Duncan, do you have a question? Didn't you email me something? All right. I take it back. Anybody else got a question? Well, there's definitely something you can think of, should think of, and that is what if V2 plus is not 0, or V2, then that's a question I thought I was going to get today, but since I didn't, and I thought I'd give you a problem with that. Do you all do the problems? This? All right, you can look at page 560. This is example, it's a drill. Is it a drill? No, this is example 10.4. And this is kind of a good problem. It's kind of wide open, too. Suppose I have this. I have a characteristic impedance of Z naught. Then I have my S parameter matrix in here. And then I just put a dead short on port 2. Now what happens to the S parameters? Remember, I have known S parameters, right? Now what happens when I put a dead short on that one? Now, I want you to pay attention to this. Your gut inclination is to say, well, V2 plus is 0, right? V2 plus V2 minus. The superposition is 0. You have both a transmitted and a reflected signal at port 2 that's summed to 0. Do you follow me on that? So this, you could actually call this position 0, just to make it a little more clear. So I know that V2 plus V2 minus are equal to 0. That's the controlling equation, right? Now with this one, when we go ahead and we take a look at S11, the definition, S11 is V1 minus over V2 plus, given that V2 plus is 0. But that isn't the case. And I want to mention one. Pardon? I mean V1 plus. Pardon me. Thank you. That's not the case. As a matter of fact, let me just. And now I'm going to write down the actual, this is the definition of it. But if you look at this from the fundamental definition, I know that V1 minus is equal to S11 V1 plus S12 V2 plus, and I know that V2 minus is equal to S21 V1 plus S22 V2 plus. Those are the fundamental equations, right? Now, if you look at this with respect to, remember, we had S11, S12, S21, and S22 for this system before we actually shorted that out. Now when we do this, V21 is plus V2 minus is equal to 0. That's V2 plus is equal to, and then in this case is minus V2 minus. Y'all follow me? I defined what V2 plus was. And then I come over here, right here, to equation 1. And I can say that V1 minus is equal to S11 V1 plus S12. And then it's going to be minus V2 minus, or minus, sorry, make this a minus V2 minus right there. And V2 minus is equal to and that
Wouldn't it be minus S22 V2 then?
what'd you say?
Wouldn't it be minus?
You can, I'm sorry, I can do it right here. Yeah, this is, I should put in minus, you're right, minus V2 minus, and then I can take that and say that from there, I'm going to have V2 minus 1 plus S22 is equal to S21 V1 plus, and then I get V2 minus over V1 plus equal to S21 over 1 plus S22. Here's what I did. I was writing these sequential. I was looking for a different way to do this, but this is V2 minus is S21 V1 plus, normally plus S22 V2 plus, but because V2 minus is, or V2 plus is minus V2 minus, I substituted that in. Then I factored everything out. Then I get V2 minus over V1 plus equal to this, and that should be what he has. If I can just take a look for, does he give that one? Oh, he only wants the reflection coefficient. I'm sorry. He's just looking for the reflection coefficient, and therefore here he takes this one and he just replaces this with minus V2 plus is equal to S21 V1 plus S22. Wait a second. That's not going to give me the reflection coefficient. That's V2 plus. In terms of V1 plus, that won't do that. Let me take one quick look at this. Hold on. He just wants reflection coefficient. Never mind. So this is going to be, for this one, I can take this to this side, and I get minus V2 plus times 1 plus S22 is equal to S21 V1 plus, and therefore minus S21 V1 plus over S22 plus 1 is equal to V2 plus. And then I'll just tell you where I'm going with this. I'm looking for V1 minus over V1 plus based on this condition right here. Because the only thing he cares for, the only thing he wants, he doesn't care about any port parameters. He wants the reflection coefficient at port 1. So with that in mind, once I have this, then I go back into this equation and I just replace V2 plus with this, because now it's in terms of V1 plus. And then I can say that V1 minus is equal to S11 V1 plus S12, and then it's going to be times that, which is making this minus right there. And then it's going to be S12 times V2 plus, and then it's going to be minus S21 V1 plus over S22 plus 1. I took that and I stuck it in this equation, and then I rewrote that equation over here. That's what I'm doing. It's just manipulating at this point. When I get down to that point, now I'm going to get, I'm going to divide everything by V1 plus, so I get V1 minus over V1 plus equal to S11 minus S12 S21 over S22 plus 1. And that is the definition of reflection coefficient at port 1, and that doesn't assume anything. That is the fundamental definition. And that's what you can get. But I wanted to do at least one where the actual V2 plus was not 0. Here it's not, and the thing to remember is anytime, if you had something like this, if you had a transmission line here with some length, say L, and then there's some beta in here, and then you have a termination, say the termination is a short, all right? Well, your condition is, what it would be what you take a look at this is, any signal that comes in here, right, that's V2 minus, right? It's going to come, it's going to be delayed by, when it hits, if this is V2 minus here, pardon me, right there, at this point, as the signal's propagating, right here, you would get V2 minus, right, then it would be times e to the minus j beta L, where that would be L. That's phase delayed to that point. All right. Now when it hits this, it's multiplied by the reflection coefficient there, which is minus 1. Do you follow me? So you put a minus then it comes back around. So there's another L, e to the minus j beta L. And that meant that V2 plus would be equal to V2 minus. That's V2 minus here, comes down. It goes a distance of L, so there's a phase change of e to the minus j beta L. Is everybody with me on here? Now it hits this. That's a short. The reflection coefficient at that point is minus 1. So now I have to put a minus sign in front of there. It's going to be minus this times e to the minus j beta, and now it comes back, so it's another L, and it would be 2L. And that would be V2 plus. Do you all see that, class? And then you would use that, just the way I used that other information, put this right here into the second equation, and now you would have, see, you would have V2 plus here replaced by that, and you could get at it that way. But this is, you have to understand that. Weren't some of the other ones, didn't they have terminations that were not perfect matches in some of the problems I gave you or not? How many did the problems just level? If you did them, wasn't there at least one or two that had them different? No? All right, well, that's ideal. Most of the time in the real world, I mean, this setup right here that Wentworth had, where it was a short circuit right there, that's used for It's called calibration. Now, what I did here, you see how I basically figured out what the phase change would be because of propagation? A lot of times when you have S parameter devices, you stick them there, but you don't want port 1 there. You want it right here. So you'll add a phase change. In other words, the S parameters, original S parameters, the S11 will have, it'll be multiplied by a phase change of a wave hitting and coming back, which will be e to the minus J2L, J beta 2L. All right, and here, same with the S22 parameter. I almost feel like doing that one. Does anybody have any other questions about this? Because we're supposed to do a review. We're spending a lot of time on S parameters. Any other questions about this? All right. Any questions about prior topics? Rotate it in, L section matching. Anything, guys? I'm trying to do due diligence here and give you a fair shot at this. Nothing? Yeah. Yeah, sure.
Just for the test, are you looking at 4 or 5 questions?
I haven't made it up, but normally 4. But I mean, there are multiple parts. So, don't ever think. People do that, and it's like irritating. There are going to be many parts to these questions. Now, there's maybe 4 major topics. It could be 5 if they're just shorties. If you're trying to guess what's on the test, a pretty good indication is where we spend time and homework on. I'll not give you something crazy. I can promise you that. I know that I gave the waveguide thing with the input impedance last time. That was a little bit unfair. I thought I had assigned some homework that didn't somehow get posted. It was related to that. So that's why there's a big point adjustment. Which one did you have in mind?
I guess 8.47.
Go ahead.
A half-wave dipole transmitting antenna centered on the z-axis, orientated in the z direction.
Mm-hmm.
Shown in the sketch, we get the antenna going up and down the z-axis, and we get a little circle halfway down the line. Here.
Oh, yeah, I got it. So it comes out, and this is a loop, right? It's the radius, or whatever dimension they give.
Shown in the sketch, you place a small loop antenna 100 meter distance to receive max power. The loop antenna has a 2 centimeter diameter. Calculate the power transfer ratio for the maximum power transferred case at 800 megahertz.
All right, they want the power received, right? We know how to do freeze. You can memorize freeze, but I like to go through this from start to finish. So first of all, what do they give me about the power here? Anything about the power transmitted? What do they give me as far as? All right, they want, so if this is total power is PT, right? Is that what we're saying? Transmitted power is PT, right? All right, we're going to assume this. I'm assuming PT is the transmitted power from that half-wave dipole, okay? Now, please work with me on this one. I'm going to try to help you here. I'm saying this is the assumption right here. I'm assuming this. Assume this PT in watts. Now, if I have that, I know that the average power density at any given range R, the power density here, that would be equal to the total transmitted power, which is assumed, PT, over 4 pi r squared. I try to get people to do this. Now that means if it's an isotropic radiator, that's what it is. If there's no focusing effect. Right? Because the 4 pi r squared is just the surface of a sphere of radius r. It's equally distributed. Now you multiply it by the gain of the antenna. The gain of the antenna, I'll just call it G1. The gain of antenna 1 is a function of angle and radial distance. I'll put that in there more completely in a second. Everybody follow me? Now, it's coming, and then it is incident on this antenna, right? Well, that means the aperture has to be found, right? And if you remember that aperture of an antenna is equal to lambda squared over 4 pi times gain of that antenna. You all remember that? Please do. Please remember it. So now I'm going to just put this as gain of antenna 1. Therefore, the aperture of that is lambda squared over 4 pi. And it's times gain of antenna 2. Now I'm going to make sure, you're going to have to know the half-wave dipole. The loop antenna has a gain of 1/2. Any short dipole or small loops have a gain of 1/2. Do you understand that, everyone? They have different radiation resistances, but the gain is 1/2. Or I should say the directivity, but you can assume perfect efficiency and say gain is 1/2. Got me on that? 3.5, sorry, 3.5. It's a half above 1. I always think with that. It's 1/2 better than an isotropic, so it's 3/2. I'm very sorry I said it that way. So I know gain of 1, max gain of 1, is equal to max gain of 2, and it's equal to 3/2. Are you with me, guys? Which is not great gain. It's only 0.5 better than an isotropic, which is 1. So this one, when I want the actual P average received to P transmitted, oh, I'm sorry, this is for short. I'm sorry, this is for that is a short dipole. That's a small loop antenna. I'm bad about that. I'm sorry. For this dipole, the half wave, the gain on this is equal to 1.64. My bad on that one. The gain on this loop right here is equal to 3/2 or 1.5, and I'm very sorry about that. You're absolutely right. This is going to be gain of 1 is 1.64. Gain of 2 is going to be 1.5. So here, the actual power received, let me just do it this way. P received is going to be P transmitted over 4 pi r squared. Then it's going to be times the gain of the transmitting antenna, which is 1.64. Then it's going to be times lambda squared, and lambda is C over F. F was 800 megahertz, so it's 3 times 10 to the 8th over 8 times 10 to the 8th, so it's 3/8, right? Lambda is 3/8, and this is going to be lambda squared over 4 pi. And R is 100 meters, by the way. R is 100 meters. And then it's going to be gain of the second antenna, which is 1.5. And therefore, if I divide by the power transfer, this is what I get. I'm sorry about that. So, and the way Friese writes it is simply what? It's going to be, he's going to have lambda over 4 pi r squared times gain of first, gain of the second will be equal to P received over P transmitted. That's how he does it. Can anybody give me that? Let's see if it's the same as the book.
This is one of your problems.
Okay, what is the answer? What is that answer, first of all, right there?
The book says 219 times 10 to the negative 9.
Did you punch that out? 200 what? 10 to the 9th? Okay. You asked about that. Is there a second part to this? Here's something to think about. What if I take this loop antenna right here? Right? Now that loop antenna has a given resistance that you can calculate. I wouldn't expect you to memorize that. I would give you that calculation. Or I'd give you a value for it, all right? Probably I'd let you calculate it. But if you calculate the resistance here, so now this antenna is going to have an R antenna, right? Right there. It could have a J value too. Are you with me? So that there would be an antenna resistance that's related to the propagated signal, and there could be an antenna reactance, right? That has nothing to do with propagation. It has to do with inductive energy that's localized, and it goes back and forth, sloshes back and forth. But now if I did this, if I took that second antenna, and for the sake of argument, say I wanted to know how much power would be transmitted to a load of, say, R equal 10 ohms. Good for you. All right, 10 ohms. So I've got to attach that loop antenna, and therefore the loop antenna, the thing I need to put here is the R antenna, right, and plus JX antenna here, right? And then what do I need to do? I have to put my plus to minus V open circuit voltage there, right? Y'all remember this, right? Now this is I'm trying to bring you into a problem that's a possibility, maybe more than a possibility. With me? Now this is something you're either going to calculate or be given. I don't expect you to memorize what the radiation resistance is for loop antennas, all right, at all. As a matter of fact, complicated things like this, I will provide the information for. But you have to understand how to use that information. Now, yeah?
We have to worry about utility antennas.
If you mean, there's two, you're talking about the effect of polarization, I think, right? He's saying if you have two antennas like this and I do one of these guys like this. No, not on this test. But you got to understand, I can do this. So effectively, it looks like I'm tilting one this way, if that makes sense to you. So if they're here, now all of a sudden, the angle could be 45 degrees, you follow me? And then the gain would be reduced by the, depending on the antenna pattern, it would be reduced by the square of the electric field's value at that point. Or you got to be careful about this. This is a power reduction. Also, the aperture of the receiving antenna would be reduced by that value, right? How much the gain is reduced. Do you all see that, class? And I've given you problems like this. I know I have, where I've had this. Actually, it's one's in Wentworth's book. Do you all remember those things? So that's fair. But I want to stick on this topic right here. How do I go ahead and get VOC? Do you remember? When we talked about P received, that was the power received by the antenna assumed it was into a matched load. Correct, class? Then we went and we said, well, VOC right here was what? We proved it was square root of 4 times, that's right, R rad, times P received. And then you would put that there. After that, you would go ahead and get the current, right? You could get the current if you want. Just add this and this, right? These two impedances and divide them into the voltage. You got the current. Once you get the current, take the magnitude, the current, square it, times the resistance. Now hear me on this one. If this load had a real and an imaginary part, still you get the current. Just square the magnitude of the current, but then you only multiply it by the resistance. That's the only thing that absorbs power. Do you understand, class? That's the only thing you worry about for power delivered to the source. These are fair problems, and I'm just telling you, you should know how to do these things fairly easily. What other questions? We did EMC stuff, Ron. We've got shielding. We've got wires and filters, correct? Bodie plug, yeah. I'm not going to ask you for a Fourier transform. Not on this test. Maybe on the final, all right? But not on this test. There's not enough time. It's a 50-minute exam. People can get lost in that stuff. 2.5 hours, they can spend some time getting lost. And they can come back. All right, how about anything with EMC? We got a few minutes, guys. Anything? Electromagnetic compatibility. What we talked about is first wires, right? In a nutshell, a wire, solid wire, a DC, right, has a given internal impedance and a given resistance. Do you all remember these things? They're very straightforward. What?
Can you memorize the equation for this?
Well, there's, you shouldn't need to memorize them, but you got to know them. I mean, if you think about it, if you have a wire of a given length L, I'm going to just show you when I'm talking about how easy these are, and a cross-sectional area A. All right, if it's a round wire, the cross-section is pi times A squared. Now, that's something I expect you to know with, and not worrying to commit to memory. The resistance of this, if this has a conductivity sigma, R DC is just proportional to the length of the wire, inversely proportional to the cross-sectional area, and inversely proportional to sigma. Now that you have to know. Do y'all remember this? All right, now if it's a high frequency signal, then RAC, assuming the skin depth now is less than the radius, RAC typically is L over, now it's 2 pi, right, A times the skin depth instead of just the cross-sectional area times sigma. Remember, that's RAC. Y'all remember this, guys? This is the resistance of the wire. Then we talked about the internal inductance, the DC inductance per meter, and that was equal to simply, remember this? Anybody? Mu 0 over 8 pi 4, and that's per unit length, so it's times L technically, isn't it? That's per meter, times L would be the amount in a meter. Then there's the LAC, or the high frequency, assuming, and that was equal to really LDC, it's this, and then it's 2 times the skin depth over A. Y'all remember that? We went through that. So that's internal inductance, not external. Then we went through the external inductance for things, and then we talked about, when we went through there, that's for just a wire, right? And we talked about partial inductance. I'm not going to test you on partial inductance, just so you know that. I don't expect you to spend a lot of time on that. That's a complicated subject, far above what we can do in this class. We talked about what? We talked about how a capacitor, resistor, and inductor looked at high frequencies, right? And how to extrapolate the values from plots. Do you remember that? The standard wire did this, looked like this, right? And then what happened to a wire? Huh? It goes, normally it goes down, hits a resonance, then comes up, right? Then we did an inductor. An inductor looks like this, right? It's the V. And we did a capacitor, right? I mean, y'all remember the capacitor? So, okay. Enough said. You know what those look like. Then we talked about, then we did some stuff where we had, we're not going to do a Fourier series, but I didn't want to mislead you. You are responsible for, like, if I ask what the sixth harmonics its value is in dB microvolts per meter across a capacitor with a certain circuit's rise time and with a certain frequency and a certain duty cycle, I expect you know how to do that, okay? That's fair game. I gave you a lot of problems with that. We did a lot of talking. But not a Fourier series expansion of a signal. I don't want you to worry about that. Taking first and second derivatives to get impulses. Yes?
When are we going to get Friday's quiz back?
Come upstairs and I'll give it. Oh, I got a class now. See me after 2 o'clock and I'll give them to you, all right? I'm sorry if I didn't get them back to you. How many got Friday's quiz? No, nobody. Why should? Can you do me a favor? All right. I'll put them outside my office. I got a ton to do. Could I get them to you tomorrow? Just come by. They'll be outside my office. And I apologize for not getting them today. I've been getting stuck with meetings out of my mind.